these are called trigonometric identities. These are kind of a weird concept. So let me start by illustrating a difference between an equation and an identity. Here's an example, if my board works, there we go, of a trig equation. 2 sine theta minus 1 equals 0. Could we solve this for theta? And the answer is, well, hopefully you have those skills by now. You could add 1 to both sides. You could divide by 2. And then I'd ask you, well, where is sine of theta equal to 1/2? And then you would say, well, it's equal to 1/2 a lot of times. For sure, your calculator will give you one answer if you inverse sine it. And I'm thinking it's 30 degrees. Okay? But 30 degrees is not the only answer. There's actually a lot of answers. Okay? That is an equation where there is at least one answer. This is going to sound weird at first. A trig identity is an equation that is true for every angle. If I were to ask you to solve for theta, the answer would be every angle. So the answer would be 1 degree, and the answer would also be 2 degrees, and the answer would also be 3 degrees, and the answer would also be 1.4 degrees. And that sounds really crazy off at the surface of things. Okay? An identity is an equation that if you were to solve for theta, the answer would be everything. Every angle would work for some reason.
Whereas an equation?
An equation, they're going to look the same, by the way. An equation and an identity will look similar. I know, bear with me, okay? They will look the same, but if you were to actually solve for theta, you'd discover that every theta, every possible angle out there, 1 degree, 49 degrees, 37.2 degrees, every angle would work. I know.
Wait, but an equation.
But equation, there's only like some answers. Okay. Let me give you an example on this next slide. I'll come back to the other one here. Here's an example of an identity. This right here is an identity. Okay. And I've shown you this before here. Here's a graph of sine in yellow, and here's a graph of cosine in blue. Okay. How do these graphs relate to each other? And I gave the analogy of a sine graph is a cosine graph that, no, a cosine graph is a sine graph that failed a grade. Because basically it's backwards by 90 degrees. Here's an identity. If you want to find the sine of some angle, it's the same thing as the cosine of that same angle, backwards 90. This should work for every angle that you want to look for. So give me an example of an angle. Give me a number.
40.
40, sure. Take your calculators and type in sine of 40.
In degrees.
In degrees, yeah. Let's make sure we're in degrees. 0.6. Okay. Then do the cosine of 40 minus 90. Now, the way an identity works is that every number that you use, this should be true for. So you try 7, you try 19, and you try 1,000,000,000. It won't matter. This side of the equation should equal this side of the equation for every single x value in existence. And it's not so much an equation that you're solving for x, it's more of a property about how these things relate to each other. Basically, a cosine graph, the x value, if you subtract 90, is the same thing as the sine graph. This value here is backwards by 90. This value here is backwards by 90. This value here is backwards by 90. Does that make sense? So I don't care what x value you have, the cosine value of it is the same thing if you go backwards by 90. Here's another one. This is just the opposite way. A cosine value, then, is the same thing as a sine value plus 90. So to take this cosine value right here, it's the same thing as a sine graph moved this way. So again, my goal in this equation here is not to solve for x. That's not the point. The point then is to use these rules to do something else. Does that make sense so far? Okay. There are many known trigonometric identities, and essentially they're equations. But the point of the equation is not to solve for x. Let me find you a good example. Here's one. This is a known trigonometric identity. The cosine of 2x is apparently the exact same thing as cos squared minus sine squared. I'd like to prove that to you with a calculator. If you have your calculators. Whoa, we're doing stuff in 20-1 here. Look at this. let's say I were to type in cosine 2x as one of my equations. And then as the other equation, you have to use brackets here. You're going to have to go bracket cosine x, double bracket, then squared, minus bracket sine x, double bracket, then squared. So essentially what I'm doing is I'm making this be one of my equations and this be the other equation. These graphs will exactly overlap everywhere. Okay? And I could check that by pressing graph and find the right window size. So let me change that. Let's go 0 to, what am I in? I'm in radians. So since I'm in radians, I'm going to go to 2 pi. And then I'll go from, like, say, -5 to 5. And if I were to make it so that one of these graphs, like the second graph, becomes bolded, what you discover as it graphs is here's the first graph, going along its merry way, and the second graph should go exactly on top of it. Does that make sense? What was that?
Where do you make your range?
I went 0 to 2 pi, but that's because I was in radians. If you're in degrees, go like, say, 0 to 360. Another way of looking at this would be to go to the table of values. And do you see how these tables of values exactly line up with one another? Like exactly. Let me try it with one more of these identities here. Let me pick another weird one. Let's do one that's easier to type in. Let's try this one right here. So on one side of the equation, type in cosine squared x. So to type in cosine squared x, you have to do bracket cosine x, close bracket, and then square it. And then for the other half of the equation, go 1 minus bracket sine x, double close bracket, squared. And if I were to go to my table of values, I don't care what value of x you use, both of these graphs are always equal to one another. Does that make sense? So big difference here. If I give you an identity equation, our goal is not to solve. Our goal is not to solve for x. The reason why is that every x value in the world is true for this equation. So the point is not to solve. Usually the point is to do some really weird rearranging. Okay. And I'll give you some examples in a little while here. Does that help like solve some of those like first weird looks I was getting when I told you every answer fit? Does that make it a little bit better?
Well, you know.
Okay.
Like you could plug any x value you want and it'll give you the exact same thing as like the sine.
Yeah.
Okay.
Yeah.
That makes sense because the
Which-
first one is just 90 degrees from that.
Right. Now, what you just said there is actually the trick to how we're going to solve multiple choice diploma questions. Actually, why don't I skip ahead to that? Okay. Here, if you fast forward, like way in your notes here. Yeah, where's a good one here? Here we go. Can you guys find this one?
I was looking for two words. Question of what? So like the last page.
Yeah, like way in there.
Like second last
Okay.
page.
One of our goals is going to be, I want to show you how to algebraically figure out how to convert this thing into one of these four answers here. But what you could do is just choose an x value. I don't even care what number you pick. 1, 2, 5, 19.2. And if you, well, okay, actually I'm going to give you one suggestion. Don't go with 0. And the reason why 0 sometimes doesn't work is that this guy right here has fractions.
Oh, right, okay.
And often always, fractions can't have a 0 on the bottom of an example. So 0 is sometimes a bad number to use. Okay. But what you could do is plug in x as, say, 3 and x as 3 and find what this thing equals as a decimal number. And then you could plug x as 3 in here and here and here and here and see whether it equals the exact same decimal number. Or a 3 here or a 3 here.
That's it?
That for the diploma, that's going to be it. That's like the easy way of doing it. So when you want to do tan squared, you're going to have to go like tan of 3, enter, and then square it. Or you could do it like this. First bracket tan, x, double bracket, then squared.
Wait, those are different answers.
Are different. Why are they different? Oh, because I didn't actually put in 3.
Oh.
I need, apparently it thinks that x is 6.28. I think you can program letters to be certain values in your calculator. So apparently my calculator has programmed x to be 2 pi for some reason.
I'm really confused.
Yeah. Right. Can we come back to this though?
Yeah.
I'd like to do this last. So this will be the easy way of solving a diploma question. This will be simultaneously the worst thing you have to do ever, but on the diploma, it will probably be the easiest thing you have to do. Because I can show you a really... Plug in a random value and see which one makes it work. Okay. Did you get it to work?
Yeah, D worked. I didn't want to do A because that looked really like hard, so I
Yeah.
started doing first.
Well, that's actually not a bad idea. You could plug in, I mean, if it doesn't actually equal 1, that's off the list. And then check the other 2, and if it wasn't those ones, it's got to be A by default.
Hopefully.
Hopefully.
Maybe check that too.
What did you get as like your decimal answer?
Well, because I used 5 and then I got like 12.4278. All that. Because I like
Yeah,
I
I
used
used
3.
three.
Well, because for the
different number.
yeah. Did you like did it match though?
I don't know.
Can we come back to that later? I will go back to that later, but I want to show you guys the algebraic process for a couple of reasons. Okay, one, I want you guys to actually have good fundamental math skills, not just good diploma writing skills. And 2, this actually does matter if you go on in calculus. Okay, so I mean, if you are planning on going further on here, these are good skills to have. So here's your formula sheet. Okay, these are the identities that I need you guys to know how to work with over the course of the next 2 classes. Okay. To be honest, once you know how to work with any identity, it's really all the same thing. So I'm just going to break them up into sections. Okay. These guys right here are known as reciprocal identities normally. Okay. These guys right here are also a section that we're going to work with. These guys right here, along with the tan ones over here, are kind of a section of identities, and then these guys are the last group. So I'm going to show you how to use some of them in stages. Okay, so let me show you an example here. I'm going to just hop ahead to here. Our goal is going to be to prove that these things equal each other. Now, if I wanted to do this on a diploma question, I would just pick a number for theta, like 7, plug it in, and both sides should equal each other. Okay? But that's not doing it algebraically. Okay? So here's how you might do it algebraically. I've got some hints for you back on a previous slide here. Here's some hints. First hint. I may have to do the first one, by the way. Like actually just show you how to do one first. But here's some hints I have, though. Begin with the more complicated side. That may sound weird to start with the harder looking side, but it's actually good advice. Okay. Look at the whole identity and figure out whether there are any direct trig identities you can work with. Change everything to sine and cosine. Factor if possible, and sometimes you can use conjugates.
What's a conjugate again?
Yeah.
When it comes up, I'll show you.
Okay.
Well, okay, a conjugate is if it's like 1 over x minus 2.
Oh, right.
It means you times by x plus 2 over x plus 2. This is a conjugate. If this guy is a negative sign, you times by his positive doppelganger.
To cancel. Okay.
When it says to change everything to like cos and sine, does that mean that we can just cross out the tan?
That's actually going to be the first identity I use. Can I just do the first example? I think that's probably the best way of trying this, is just me doing one. Okay. Which of these 2 sides would you say looks more complicated? Okay. And sometimes old diplomas, they used to ask that you'd like do stuff on the left-hand side and the right-hand side, which is how that diploma question was phrased for you. So the right-hand side here of 1 minus cosine over sine, I'm just going to leave it there for now. By the way, when I do this, I don't ever write theta, because I find that that's redundant because everything is theta. So I'm just going to skip writing theta, if that makes sense. This side over here, though, the tan stuff over here, one of the things I could do is use an identity about tan. And so if you go back on your data sheet, here is an identity about tan. tan could be written as sine divided by cosine.
So then just work tens with that.
Perfect. So that's the first thing I'm going to do. Wherever I used to have tan, write sine over cos. So it'll look like this. Sine over cos minus sine over, and then rather than this tan right here, I'm going to write this guy as sine over cos times sine. So I used the identity of tan being sine over cos. So far, so good? All right. Well, now my goal is to manipulate this side so that it looks like this side over here. And we're not to that point yet. Okay. The bottom of the fraction is probably okay the way it is, but the top of the fraction actually has two different terms. And one of the things we can often do with terms is give them common denominators. So what I could do is put a cosine here and a cosine there. And now they actually have common denominators. Just the top, though. So what I could say then, in my next step down, is I have sine minus sine cos over cos over, and then this guy right here as a fraction, I could write it as sine sine over cos.
Can you slow for a second?
Absolutely.
This is like.
Good. So let me re-walk you through those three steps I did. The first step was I said tan is actually, rather than calling it tan, let's call it sine over cos. Okay, that's step one. Step two was this minus sine right here. Now that it's a fraction minus sine, I made it common denominators by putting cos and cos right here and here, so that I now have common denominators. And then in this next step here, I actually put those denominators together. So this top of the fraction is sine minus sine cos over just a single cos. That's what went here. But these guys were multiplied. So really this is like a sine over 1. So on the bottom of the fraction, you have a sine sine over just 1 cos. Does that make sense so far?
Yeah.
Next twist.
Yay.
Okay, yeah, that makes sense. It's like the last question of
I mean, this is something over cos over something over cos. Isn't cos in the bottom of both fractions? So what I'm left with then is this. Sorry, I'm running out of room here. You have sine minus sine cos over sine sine. Close. Not quite yet, though. I have to factor first.
Knew it.
So then the top of this fraction right here has a sign on both terms. So I can factor out the sine, and it would leave me with 1 minus cos over sine sine.
Here, wait, sign what?
Okay, let me slow down again. So this guy right here.
One of them cancels.
Yes.
Okay, so it's one.
Okay, cool. You've got it. Let me go back here.
Oh, I see
Okay,
that.
good. The top of this fraction right here, do you see how this is a term right here? And this is a term right here? Sorry, guys. Sorry.
Why is
It's
it
my
one?
wife. Hey, sweetie.
So it's a negative.
Hello?
So it'd be like sine and then
Yeah, like how
I have no idea. Can I call you back? Can I call you back later? I'm kind of in class. No, sorry, love. Okay. Thought it was an emergency. Nope, TV wasn't working. It's the only reason I answered it. I'm like, what if one of the kids is going to the hospital? I should answer it. Why is the TV volume not working? Sorry.
It was an emergency.
I thought it could be. Sorry, guys. Okay, going back here, this sign and this sign, both of these terms have a sine sign. So I'm going to factor out the sine sign and leave it with sine equals bracket 1 minus cos. If I were to refoil it, sine times 1 would give you sine, and sine times cos would give you sine cos.
Oh.
Okay, good.
Okay.
Then this sine could cancel with one of these sine signs. and it equals the other side, which is my whole point of this thing.
Say sign.
All right,
Like,
Bertie.
no.
Are you sure?
Yes.
Okay, so couple of thoughts here then. Why do you want to start with the harder looking sign?
Because it's more likely that it'll like equal it and you don't have to do anything on it.
It's more likely that it will cancel by simplifying, if I throw in what Amy said there, yeah. So it may sound counterintuitive to work on the more difficult side, but ideally something will cancel and it'll turn into the easier side. Okay, a couple more thoughts here. You guys aren't going to have to answer something like this, because they don't write diplomas like this anymore. Okay. What they would do is they might say, this equals what? And then part A could be this, part B could be some other random stuff, part C would be some other random stuff. Pardon me. Rather than actually solving it like this, the most efficient method, and the method I'm going to recommend you actually do when it comes to the diploma to save time, is just plug a number in for theta. Any number should work, but my recommendation is don't use 0 though, because like if you were to do sine of 0, it would give you 0 on the bottom of the fraction, and that would probably cause problems. Like use like 2.3 or like 7. Did that make sense?
Yeah. Yep.
Okay. Let's go back to that warm-up question then that I just showed you there.
Oh, we can do it.
We might be able to do it now, but we have to use other identities. Because I only used one of them. There are many rules on your rule sheet that could be useful in solving things. So, can I do this one with you guys, or do you want to try it by yourself first?
I'd like you to do it.
Okay, I'll do it first. So, let's do this guy right here. Left-hand side would be this. Right-hand side would be this. We're definitely going to start with the left-hand side. Now, one of the things I could do is change everything to sine and cosine. So, there is a rule about cosecant on your data sheet. Cosecant is actually equal to 1 over sine. And there's also a rule about cotan on your data sheet, which it's equal to something else though too. You're right. But in terms of sine and cosine, it's actually equal to cosine over sine.
Wait. That makes sense.
Can you guys see that one on your data sheet? There's one on your data sheet that says cotan equals cos over sine. Nope, those are given to you. Oh, that'd be horrible. Amy.
Yes. How do you know which identities to use? Or do you kind of just spend equal to
Okay, there's a good question. Can you guys listen up for this? This is a great question. You're not going to like the answer. Amy asked, how do you know which identities to use? You don't. You could use any of them if it's helpful to you. I'm going to show you some examples maybe later where I try doing something using one identity and I discover, this is not working. And so sometimes you might try doing something, when you do it by hand, discover it's not getting you anywhere, and you kind of have to rip it up and start over again. Okay, good news though, I'm not going to make you do this very much. I want you to know how. I'm going to put it on an assignment where I want you to do it by hand, but like on your diploma, you don't actually have to do it this way. Okay? So, okay, next thought here. Now that I've actually converted these things, last time I had fractions, what did I do?
You could just put them together.
I could put them together. Yeah.
One subtract.
So I could do 1 plus cos, and this would be 1 minus cos over sine. Okay, next thought here, because I'm kind of at a stuck point here. This guy right here is also a fraction if I made it over 1. So here's why I'm going to suggest we could do that. It means that the top of my fraction now is 1 plus cosine, 1 minus cosine, and the bottom of my fraction is actually just sine. Okay. This thing up here,
Isn't that like a...
FOIL it. It's a difference of squares.
Yeah.
How do we get sine out of both?
Because it's 1 times sine. So like I did this times this on the top, and then 1 times sine on the bottom. But there's really no point in writing 1 times sine on the bottom.
Oh, okay.
So that works?
So it's like
1 minus cos squared.
Sure, that'll work. So this right here, if you FOIL it, I'm just going to write the word FOIL here, you would get 1 minus cosine squared. It's a difference of squares, basically, and it's over sine. Well, technically it is smaller. There's you used to have 1, 2, 3, 4 terms. Okay, I guess it ends up being smaller because the middle terms cancel, though. Because like when you do cosine times 1, you get cosine. You do 1 times negative cosine, you get negative cosine, and those terms cancel. So it does make it smaller, I guess. Okay, one more thought. This one I won't expect you guys to get yet, but experience with your data sheet will help. If you guys can find your data sheet, there's a rule on here, right here. It is sine squared plus cosine squared equals 1. You guys find that rule? And right here, you have very similar looking stuff, Birdie.
Minus cosine squared equals sine squared.
Yes, according to this sheet right here, if this identity is supposedly true, if I were then to, like, for example, take the cosine to the other side, sine squared would equal 1 minus cosine squared.
So with the sign on the bottom.
Okay, good. Some of you guys are getting this, but slow down for those.
How do we get from here to that?
Okay, so at this point right here, I got kind of stuck. At this point right here, I got kind of stuck.
Oh, so you multiply sin up.
Nope.
Like this?
Nope. I didn't do that either. At this point here, I look for another rule. Okay. Right here is a rule that has similar looking stuff. You see how there's a 1 right here, and there's a cosine squared, and I have a 1 and a cosine squared. Now, you guys will get better at this with it. Okay, that's okay. We're going to make it equal to sine squared. If I were to take this rule right here, I wrote it right here. Say I were to take the cosine squared and bring it to the other side. Then I'd have a new identity that would say, well, sine squared is really equal to 1 minus cosine squared.
Which we got over there.
But 1 minus cosine squared, if I go like from here to here and continue going, that's actually what I have right here. So essentially this stuff right here is sine squared. So then you have sine squared over sine. Gives you
How
sine.
can you just
Substitution. You're doing substitution.
I don't understand how you can just like hey, you want to put a sine squared right there.
Okay, well, right here you have 1 minus cosine squared. But on the other set of notes here, I said that sine squared is 1 minus cosine squared. So like, we have this right here, but rather than calling it this, I could call it this by substitution.
Okay, so then you
So I substituted this in for this. So rather than calling it this guy right here, I called it sine squared.
so it's not on the other side of the equation, it's just right there and then it's over sine and then it's exponential crap stuff.
Sure. Okay, one thought here, by the way. Some of you have mentioned this. In order to solve these things, I want to use the word like properly in quotations, in terms of like how we consider them to be mathematically proven. You cannot go across the equal side. So like, it's not considered valid to then like try to, where would it have been? Like say at this point right here, try to times the sign to the other side. That's not considered to be a valid way of proving something. I don't have a great reason as to why. Sorry. But the idea would be that you should be able to work with just this side of the equation and make it equal to this side of the equation. But you can't like take something from this side and bring it to the other side.
So it would work?
Well,
It might work.
I'm sure it would work, but we don't consider that to be like a proven properly kind of thing. So,
I have a question. Are there going to be examples, I don't know if this is like, if it works or not, but where one side is really ugly, but the other side's also really ugly, and you're going to have to make like changes to
yeah.
both?
And sometimes we do that. Sometimes when both sides are ugly, you kind of make a change to this side until you get to a certain point and you stop. And you say, I'm kind of stuck. Okay, let's work with this side. You do some stuff to this side, and then when you eventually get this side to equal this side again, then you're good. So you're like your proof almost works like this side down to here, over, back up here.
Okay. I feel like that takes a really long time.
Which is why I want to show you guys the efficient methods, but I also do want to show you, like, if you're going on in calculus, you kind of need to know these skills too. So.
Okay. Well, why can't you use hand and then why can't you use hand?
Sorry, give me a second here. Let's do that. Okay, question?
Why can't you like keep hand in it? Like why does it have to be just cosine?
Usually it works better when you just go to sine and cosine. I don't know how tan would have helped then, because like say when you wanted to FOIL, it's kind of tough to FOIL a cosine into a cotan. But if cotan was actually cos over sine, which was some more random stuff here, it usually works better when you either have sine and cosine and only have 2 variables, rather than having like 6 possible variables with like sine, cosine, cotan. Does that make sense?
Yeah.
I can try to FOIL a cosine and a cotan, but when I FOIL cosine and cotan, it's cosine cotan. Like, it doesn't make anything. Right? But if I can just work with just sine and cosine, really I'm just having x's and y's. And it's a lot easier to work with just x and y rather than x, y, z, w, p, and q.
So can you do that part of that thing again?
Sure. So like way down here at the bottom?
Yeah.
So the big twist at the bottom was right here when I got to a 1 minus a cosine. 1 minus a cosine I'm kind of stuck on, but there is a rule on your data sheet that says sine squared plus cosine squared equals 1. And if I were to play with this rule and bring the cosine squared to the other side, I basically have what I was stuck at right here. So then rather than being stuck with this, I'd rather be stuck with sine squared. Well, then rather than writing this guy, I said write it as sine squared, but then this is really sine times sine. So one of the signs on the top cancels with the sign on the bottom, and all you're left with is sine, which, by the way, is what that side was. When you solve these, and you know you've solved them, you can like hear it, because I can hear you guys having these like epiphanies where you're like, whoa, it worked. Sorry, Nicole. We'll get there. Does that make sense? The key here then, and this is where I'm going to need some time to do some more examples. On your data sheet, you need to be somewhat familiar with all of these formulas because they, and I want to emphasize this word, they could be useful in solving. But like, you don't have to use all of them. You're probably on the diploma only ever going to use like 1 or 2 of these identities. Like only occasionally they come up. But these could be helpful in proving things. How's that work so far? Can I try another example?
Yeah.
Okay. Oh, by the way, most of these rules have actually been proven using calculus. If I were to teach you guys calculus, I'd actually show you guys how these rules were discovered. But one of them can actually be done by Pythagoras' theorem. Okay. We talked the other day about a unit circle. The unit circle has to have a radius of 1. Does that make sense? So imagine you have a circle here, and I force this radius to be 1. Okay. This side right here is normally the opposite side, or we call it the y side. And this side right here is the adjacent side, which we sometimes call the x side. Okay. Sine is normally equal to opposite over hypotenuse. But if the hypotenuse is 1, then rather than dividing by 1, I'm just going to make it equal to the opposite, which is y. Cosine is normally equal to adjacent over hypotenuse. But again, if the hypotenuse is 1, then cosine is really equal to x, which means when I want to plot this point on the corner here, this point is actually cosine and sine. Okay, here's what that means then. Take that triangle. This side right here is actually sine. This side right here is actually cosine, and this side is 1. This is where what's called the Pythagorean identity came from. Cosine squared plus sine squared needs to equal 1 squared. But 1 squared is just 1, and that is where is it? This rule right here came from. I don't need you actually to know how to solve that. Like, it took mathematicians years to figure that out. But if you can understand how to use the rule, that's important from there.
Still good for 1?
What was that?
Still good for 1?
Yeah, sure.
I want to talk for me.
Okay. Okay. 12:15.
So can you go back to that slide?
Yes. Okay, so can I redo that one more time? Sine would be equal to y over 1, and cos would be equal to x over 1. Is that the over 1? Does that help things?
Yeah.
So then, rather than calling this thing opposite, really this side right here is y, so it's sine. This side right here is x, so it's cosine. And that's where the rule came from.
Is that why tan equals sine over cos?
Yep, and that's why tan is sine over cos. Good point. You have a question still? You're good? You have a question still? We'll come back to you. Sorry. Okay, let's try another.
Isn't, because didn't you just, you put cosine squared cosine squared equals 1.
That was Pythagoras' theorem then. So this square, oh, okay, it was 1 squared.
Okay, I just need to see that.
Isn't 1 squared just 1?
Yeah, I just, yeah.
Okay, let me try another one. Go ahead, Bertie.
Actually, I remember what I wanted to ask.
Go ahead.
Can I put this like, on my data sheet?
Those ones, like the ones that I found there, I found that on the internet. If you'd like to write more of them on your data sheet, sure. But the only ones that the diploma should require you to use are the ones that are actually already on your data sheet. So, sure, if you want to, I'm just not sure whether it would help. Okay, let's try this one. Of the two sides, obviously the left-hand side is more complicated. Maybe. So I'm actually going to save some room. I'm going to put the 2 over here, and we're going to work with this side here. So this is my left-hand side, my right-hand side. Okay. First idea, is everything in terms of sines and cosines?
Yes.
Okay, if it's not, that's usually a good place to start. Because rather than working with many variables, we really only have x's and y's going on now. Sine minus cosine all squared, I could actually FOIL that. See if this makes sense. I'm just going to take just this portion right here. And I'm going to write sine minus cosine next to sine minus cosine. What would happen if I actually FOILed just this bit out? Well, sine times sine would be sine squared. Then you'd get a negative cosine and a sine. But then we do the other set, you'd get a second negative cosine and a sine. So you'd actually have negative 2 cosine sines. I know, it's going to seem like you're going to have that feeling all the time of like, this is stupid.
Where the negative 2 come from?
Okay, because when you do this one times this one, you get negative cosine sine. But when you do this one times this one, you also get negative cosine sine. So therefore you have 2 of the negative cosine sines. And then cos times cos will be plus cos squared.
And there's just like double that from the other one?
Well, okay, so I'm going to do this in colored pen. That was just doing just this section right here.
Oh, that was plus. Oh.
The other one here, I'll do in purple pen. I'm just going to pop this guy down here because I need more room. Is the exact same thing, but it's a plus in between. So if I were to rewrite that as sine plus cos next to sine plus cos, it's very similar. Sine times sine is sine squared. Cos times sine is cosine. Sine times cos is another cosine. So you actually have 2 cos sines. And then cos times cos gives you cos squared.
And then the middle part
The two
of
cosine
they cancel.
They actually cancel, don't they? Because this sine and this sine will actually combine together. Okay, so you'd actually have 2 sine squareds. This cosine and this cosine would add together to give you 2 cosines squared. But this middle term and this middle term would cancel.
Okay, well, that makes sense.
Pause there. That's a key step there.
Because
So this sine that you got from the first foiling and this sine that you got from the second foiling, they'd add, so you'd have 2 of them. This cosine from the first foiling and this cosine from the second one would add, so you'd have 2 of them. But the middle term and this middle term, one is positive, one is negatives, they would cancel. Okay, one last thought then. We need to somehow make this thing equal to 2. Well, there's a 2 on both of these guys right here. So I could factor out the 2, which would give me sine squared plus cos squared. And then this is where a little recognition of your data sheet helps. We just proved, though, that sine squared plus cosine squared
Is 1.
is 1. And we've now proven that 2 equals 2. Okay. If this is something that you're good at, that's good, because like this is like a calculus skill you might use later on. Okay. If you're not thrilled about this, that's fine. Okay. Because let's fast forward then to some of the diploma questions just to finish class off. I got about 10, 12 minutes left here. To be honest, I've actually shown you the topic. Okay. The key now, though, is can you use the identities on the sheet as need be? Okay. But if we're not going to be doing that a lot, let's just practice some questions here. Here, apparently, this stuff is supposed to equal this stuff. We could try to prove it by doing all those algebra steps that I was working on there. Or what they've suggested here is, why don't you substitute 2.1 on both sides of the equation? 2.1 radians. So really what they're saying to do here is, wherever you have x, make it 2.1, make it 2.1, make it 2.1, make this 2.1, make this 2.1. And the question is, when you plug in 2.1, what will both sides of the equation equal?
So basically, like, you don't.
Yeah. So the key here, though, is you got to make sure you can actually plug this in your calculator properly. So, because that's not easy. How do you put a cotan squared in your calculator?
No, but it's.
Okay, well, what is cotan equal to?
Oh no, adjacent over.
Okay, how about another idea here? Cotan is the same thing as cosine over sine. That might make it easier. So,
And then you square like the whole.
so okay, watch this here then. I'm going to square the whole thing in a second. I'm going to go bracket cosine of 2.1, divide by the sine of 2.1, double bracket, and then I'm going to square the whole lot of it. So that takes care of cotan squared. What about cosecant? What is cosecant equal to? It's equal to 1 over sine. So then I'm going to add 1 divided by sine of 2.1. And then I'm just going to make sure I'm in radians. I got the answer 1.500. So I think this side is 1.5, basically. So I didn't do the reciprocal. I did 1 over sine. But you could do it with a reciprocal if you did this. Let me just delete some stuff here. Give me a second here. This should work as well, though. I would then do bracket sine of 2.1, double bracket, and then I'd do the minus 1 after it.
Okay, I like this.
And then you should get 1.5. What should the other side of the equation also equal? 1.5. Let me see that I can make that work as well. So that would be doing bracket cosine 2.1, bracket squared, plus sine of 2.1, bracket, and then I'm going to have to divide that all by bracket. The hardest part about this is dealing with all those brackets. 2.1, close those brackets, and then make sure that it's squared.
Yeah, I can do
And that should also equal 1.5.
Yeah, I missed the first chunk.
The number 2.1, did that matter? in theory, I could have done that for the number 7 or 19 or 42.3.
And would it still give you 1.5?
Well, it wouldn't give you 1.5 anymore, but both sides would still equal each other.
Okay.
Does that make sense? So I started with this one first because this is essentially what you're going to do if you want to try to solve a question like this in the diploma, is you're going to pick a number and plug it into both sides and make them equal to each other.
Yeah. Yes.
Yeah, we had to be in radians for this to work. Is there a chance you're in degrees? Okay. Okay, let's try another one. We want to figure out what this thing is equivalent to. So again, I could try to find some rules on my data sheet, or I just pick a number for x. A couple suggestions though. Don't pick 1 or 0, because sometimes 1 and 0, when you type it in, like the sign of 0 is 0. That's usually a poor choice. I also recommend not to use 1, but like pick a number like 2 or 3 or 4. So like cotan, what number should I use for x, just so we're all on the same page? 2. Perfect, 2. Okay. It's hard to type cotan in your calculator though. So cotan is really a cos over a sine. So I'll do a bracket, a cos of 2 over a, go ahead.
How are you supposed to know, like, when you plug this into your calculator, if it equals, like, any of those?
Well, because then we're going to have to plug 2 in for each of these x values as well and see which one is the same as each other.
In this one, wouldn't it just be easier to do it, like...
Well, it might actually be easier just to try doing it with the identities, but it might be. Don't get me wrong. You might actually want to try it that way. Well, okay, so really what it means then is cotan squared x plus CSC x minus 4 is like your left-hand side. And then your right-hand side, well, we're just going to leave it as an unknown. And then as soon as this guy turns into one of these 4, then that must be the answer. So it's a little weirder to do this step here. Okay, then when I want to do a cosecant, that's going to be 1 divided by sine of 2 minus 4. So I'm going to look for an answer that is negative 2.69, apparently. Did you guys get the same thing, or did I mess up?
I got negative 2.69.
Okay.
I got the first one.
So based on that, I can already rule out number 4, or like D, negative 4, because this thing does not seem to consistently equal negative 4, so that one's out. C looks like the hardest one to type in, so I'm going to leave that one for last. Has anyone tried A yet?
I got that it works.
A seems to work? Okay, let me prove it then. Cosecant squared would be like a sine squared, but then to make it a cosecant, it would have to be to the minus 1. And then I need another cosecant, so that's going to be a sine of 2. This one doesn't have to be squared, but it does have to be to the minus 1. And then minus 5. And hopefully that equals the same thing. So this one was nice because it was actually the first one we tested. Let's say you got stuck on this though. This one actually is a really easy one to solve algebraically. May as well do that real quick. It has to do with this thing right here, cotan squared x. Can you guys go to your data sheet and try to find an equation that has cotan squared x in it? Or just cotan squared. No, cotan squared.
One was cotan squared equals cosecant squared.
Okay, so just make sure everyone sees the same one. There's one right here that involves a cotan squared. Okay. But is the cotan squared on this guy actually by itself? Okay, so what I'm going to do is I'm going to get the cotan squared by itself by making it equal to cosecant squared minus 1. Because I'll have to minus the 1 away. Then if I were to take this guy right here, so you just have to remember this, wherever I used to have a cotan squared, call it a cosecant squared minus 1. So flip back again. Cotan squared is actually equal to cosecant squared minus 1. So then really what I have is cosecant squared minus 1 plus cosecant minus 4. But the minus 1 and the minus 4 go together to get us that minus 5 one. It may have actually been easier to try doing with identities. That actually wasn't that bad to solve. That being said, like some of these are horrible, just so you know. Why don't we do this one here? We skipped this one a little while ago. Why don't you guys try to see whether you can figure out this one? Oh, no, we did this one, didn't we? Because Heather figured this one out for us, didn't she? No, never mind then. Okay, how about try this one then? So here's a bit of a twist on the one afterwards. We give you this really crazy identity, but then we also throw the letter M in there. And our question is, how do we get M by itself?
You remember like,
So it's almost like there's like a leading coefficient there, yeah.
oh, I feel like if I do this, or would you use the other side of this one?
Okay, so what I would suggest here is, how about we get M by itself first by bringing stuff to the other side? Normally I'd say, yeah, that's not a good way of proving things, but for our purposes this will work. So what if we were to make M equal to 8 times the 4 cosecant x tan x divide by the sine x cotan x. That's what M would be equal to. To be honest, I feel like I can narrow this down. 8 times 4. I'm pretty sure it's got to be one of these last two guys then.
Okay, so how do we just also get M?
Okay, so it said what's the value of M?
Yes.
So really I want to isolate and get M by itself. So I brought this stuff up to the top of that side and this stuff down to the bottom of that side. This one may actually be easier to solve without using numbers. Because I know that's a 32 there. Can you guys give me 1 minute here? Because there was already an 8 sitting there. And then I brought the 4 stuff up to the other side. And I brought this stuff down. Cosecant is 1 over sine. Tan is sine over cos. And then cotan is cos over sine. I could cancel this sine with that sine. I could cancel this sine with that sine. And I have 2 cosines left, but they're both on the bottom actually, because this is actually on the bottom of the first fraction, and this is on the bottom of a second fraction. So what I really have left is the 32, and then I have 1 over cosine over another cosine, which is secant squared. Sorry I'm speeding up on that last one, but that might actually be the best way of solving this guy.